Okay, so today the midterm is postponed, okay, to the 14th of November. Okay, so today I will start a new chapter. Okay, so last chapter is about the ODE. Okay, so then the new chapter is about this matrices and the applications of using matrices. Okay. So in this first part of this chapter, okay, so it won't be directly related to matrix. So at the end is related to matrix a little bit, but in this part, what we are going to talk about is the so-called the systems of linear equations. Okay, so I believe that this is something that you know how to solve already, right? So but the purpose of this part of the chapter is that I'm going to try to give you a more geometrical perspective of solving this system of linear equations. Okay, so from that, we will have some intuitive understandings on some concepts, okay, related to linear algebra and vectors, as you will see. Okay, so first, okay, so here we are considering something really simple. Okay, so as I said, you must have learned how to solve this before. So what I have here is a system of two linear equations, okay, with two unknowns. Right, so the two unknowns are the x and y. Right, so I have this first equations and the second equation. So here I call this the non-homogeneous system, okay, because here I'm actually assuming that the two constants on the right-hand side are non-zero. Okay, so that's why I call this a non-homogeneous system of linear equation. Okay, so if I just look at this first equation, so or I said one of the row of this system. Okay, so what I have geometrically is a line in the xy plane, right? So then if I have considered the second row of the system, which is just another equation, right? So this is another line on the xy plane. So that's why the two rows, right, so of this system gives you two lines in the xy plane. Okay, and solving this system of equation really means finding the intersection between the two lines, right? So geometrically, that's what it means. And in this case, okay, you can see that we do have a solution, okay, which is given by this intersection point, right? So the x coordinate and the y coordinate of this intersection point is the solution of this system, right? And now, is it true that we will always have a solution to the system, right? So that's not true, actually, right? So you can see this case here, right? So this time, if I have these two lines, so happen to be parallel to each other, okay, so whether they are parallel or not, right, depending on the slope of the two equations, right? And the slope of the two equations, of course, depends on these A11, A12, A21, and A22, right? And in this case, right, in this case, they happens to be parallel to each other. And if they are parallel, but they are shifted over by a distance, then you can see that you have two parallel lines that will never touch each other. Right? So in this case, you have no solution because you can never find any intersection point. Right? So then there's actually a third possibility is that, again, I have two lines being parallel to each other, but also they overlap with each other. They just lie on top of each other. Then that means you have infinitely many intersection points, right? So any points on this line is an intersection point, right? And then this line is self-extended to, the minus infinity to plus infinity. So that means you have infinitely many solutions in the case. Right? So then I have three cases, right? And of course, which case we are at really at the end, depending on, right? So your constants, coefficients over here. Okay. So then the last page is about the so-called non-homogeneous system, right? So here I'll talk about homogeneous system, where I have the two constant on the right-hand side to be 0, right? So here I have B1, B2 non-zero number. Here I have 0, 0 to be 0 number. So again, in this case, okay, so I will be able to draw two lines, right? So on the XY plane, but the most important difference, right? The difference between this case and the previous case is that whenever you draw your line, okay, it doesn't matter what kind of slope you have, the line has to be passing through the origin of the XY plane, right? So because of the 0 on the right-hand side. So then in this case, right, so if I have two lines and they have different slopes, then it's guaranteed that you will have, well, the solution at the 0, 0 point, right? So, and now if you have two lines to be having the same slope, and also it's required that they both pass through the 0, 0 point, and that means, right, so the two lines will just entirely overlapping with each other, right? So and then in this case, again, you can find infinitely many solutions. Okay, so any point along this line is a possible solution. Right? So what about the case where we have no solution, right? So in this page, we have also a case with no solution. So you can see that actually here it's not possible for you to have no solution, right? Because as long as if you draw two lines, right, so they all have to pass through the 0, 0 point, then at least the 0, 0 will have to be the solution. So that's impossible to have no solution, right? So, and also, right, so can you have a finite number of solutions that is greater than 1? And that's also not possible, right? Because these three cases already summarize everything that's possible. You cannot have two straight lines, but then they intersect at two different points or three different points, right? So now let's actually try to generalize the situation a bit more. Is that here we consider three linear equations in three unknowns. Okay, again, I'm sure that you have solved it before, but here let's try to look at it geometrically. Right. So again, I'm first considering the so-called non-homogeneous system because of this non-zero B1, B2, and B3. Okay. So now what we have here, okay, for each row now I have this XYZ, right, instead of just XY. Right. So if I just look at one equation here or one row here, then what you have geometrically is a flat plane in the XYZ space, right? So just like this red plane here. So then I have three equations. So in principle, you draw three planes on the XYZ space. Okay. So then what does it mean by finding the solution? Well, again, we are finding the intersection, okay, between the three planes. So instead of the intersection between the two lines. Okay. So how do we find the intersections between three planes? Okay. Then first of all, let's just consider the first two planes, the red one and the blue one, right, corresponding to this red plane. and the blue plane. Okay, so I don't draw the third one yet. So, but just with these two planes, right? So if they are not parallel to each other, you can see that there will be an intersection. There will be an intersection, but that intersection is not just a point, right? Instead, if you have two planes, right, so crossing each other, the intersection is defined by a line. Okay, this line will be a straight line, and this line actually will be an infinitely long straight line that extends, the entire range of the space. Okay. So then that means this line, right, so will give you the coordinate points that satisfies both the first and the second equation. Okay. So that means your solution at the end should lie at some point in this line. Okay, but we are not done yet, right? Because now this line only represents the solution of the first two planes, but we also need to consider the third plane. Okay. So the third plane is the green plane that I draw here, right? So, and then I also take this line that I had from the first figure, right? So to this second figure here. So then now we are finding the intersection between this line, which is obtained from the left-hand side, and the green plane itself, right? So then you have a line and a plane, then it's possible that you have intersection point, right? Just one point now. Okay. Then this point here indicated by the red dot is the solution of this system. Right. So, and this is actually the case where we have just one solution, one unique solution. But again, we have the two other possible cases, right? So the no solution. So how does no solution could occur, right? So is that if I take the line of intersection from the first two equations again, and then we also consider the third equation here. And if you realize that this line is actually parallel to this green plane, but they are shifted, okay, by some distance, then you know that you cannot find any solution, right? So for this system, okay, so this is the case where we have no solution. So, and also it's possible for us to have an infinitely many solution. Again, if I have the line here, and this time if you find that, okay, so the plane is again parallel to your line, but also is overlapping with your line. So that means this line and this plane will be touching each other at infinitely many points. Right? So then this is the case where we have infinitely many solutions. Right? So again, we have three cases. Right? One solution, no solution, infinitely many solution. And of course, right, so you have, when I say that the first two equation give me this intersection line, of course, I already assume that these first two planes are not parallel to each other, right? So, but you could imagine that you can have a case where the red plane and the blue plane are already parallel to each other and are shifted, right? So then in this case, right, even just from the first two equations, you know that it's not possible for you to have a solution at all, right? And also, if you may also find a case where if you look at the first plane, okay, and you already see two planes that are parallel to each other and then exactly overlap with each other, then just from the first two plane, you see that, okay, in this case, you are having infinitely many solutions. Right? So now, again, homogeneous system, right? So that means, again, I have this right-hand side to be all zero. Okay. So this times, again, I have three planes, right? The red, blue, and green, but then this time they all have to be passing through the origin, right? So no matter what orientation you have for each plane, right? So but since they all have to pass through the origin, so then you at least will have solution, right? So which is again at the origin of the coordinate system. And the other case is that you can have infinitely many solutions. Okay, so that means that after you consider the intersection of the three planes, you don't find that it's just this point at the origin, but instead it's an entire line like this, right? Or you could even imagine that if you have three planes that actually parallel to each other, right? So then the entire plane is also give you infinitely many solutions. Right? So again, so two cases, right? Again, similar to the 2x2 system, this is impossible to have no solution, right? So whenever you have the homogeneous system, not possible to have no solution because the 0, 0, 0 at least is the solution. So then this is one of the geometric way to look at the problem here. Okay, so the microphone is running out of battery. Let me change. Okay, so I hope the people in the Zoom section can still hear me clearly. Okay, if not, please let me know. Okay, so now we are going to use another way to look at the same problem. The problem, the picture that we have just used is known as the row picture, right? Because we are considering each row of the system of equation to be a geometric object, right? So which is a plane or a line. So then the next, the other way to see it is known as the column picture. Okay. So here, instead of treating a row of the system as a geometrical object, here I'm treating this column here, so this column with these two constants as a geometrical object. And then these two numbers in the next column to be the other geometrical object. Okay. So in this way, okay, so this system of equation can be written in this form. Okay, you can see that this, I call this a vector equation because you can see that I have this number times this column vector with two components plus another number times the other column vectors with two numbers, right? So equals to this B vector with again two numbers. So then in this so-called column picture, right? So this one is a vector, this one is a vector, and this one is a vector. So each column give you a vector. So then again, try to look at it geometrically, right? So here, A11, A21 will be represented by this red arrow, which is the red vector in this XY plane. Okay. So, and then the other one, right? So A12 and A22 will be the other vector, this blue vector here. And then this B1, B2 will be this black vectors. So previously, when we look at this, right, so in the row picture, we are considering two lines, right, intersecting each other. So now, okay, we look at it in this way, is that I want to have the first vector, okay, multiplied by some factor x1 plus the other vector multiplied by some other factor, factor x2, such that this sum will give me this b vector. So that's what happened in. I take my message. 1.8之前掛8號風球，我哋呢度係上到1.3嘅，但係其實我講完呢度，可能我今日即係早少少完嘅，如果好1點前可能佢係確定咗1.8掛8號係咪 ？Okay, so here, right, so as I said, right, so I'm going to have this sum to be this vector, right? So this vector is this red solid, right? So multiplied by this x1 is make it longer a little bit, so given by this red dashed vector here, okay? And then this blue vector is this one, and then multiplied by this x2, then it makes it longer, right? So it becomes this dashed blue vector, and then by this parallelogram rule, right? So you know that this vector plus this vector give me this b vector. Right? So then we find the solution, right? So to this equation, right? So the solution is that you need to select the appropriate x1, which is the scaling factor of this vector, right? And then the other scaling factor is x2 for the other vector, such that, right? So these two vectors add together give you the black b vector. So then this is a case where we have one unique solution, right? So and then the other case, okay, so this is really also just one solution, but you see that the two vectors are pointing in different direction, but at the end you can find the corresponding parallelogram to make it work. So then in these two cases, you find one solution, and that solution is unique, and you can see what is the common feature of these two cases is that your red vectors and your blue vectors are not parallel to each other. Or as I will introduce, and I also mentioned last time, is that these two vectors are linearly independent. Okay. So now let's look at the next case. Okay. So again, solve for the same vector equation, but this time you see that my red vector and blue vectors are parallel to each other. Okay, and you can see that the directions are not the same as the direction of this black vector. Okay. So then in this case, geometrically, you understand that you are not going to find your solution anyway, right? Because no matter how you add up these two vectors here, the direction that you're going to point is go to this direction. But you're never going to get a vector that points in this direction. So therefore, in this case, there's no solution. So, and also, okay, one more case here is that again, this time I have two vectors parallel to each other, this red and blue, and they happens to be also the same direction as this black b vector itself. So in this case, of course, you will have a solution, right? So you can add up some blue and then some red and then get to the black. Okay. And in fact, in this case, you have infinitely many solutions. So I guess it's not surprising to you. So because let's say if this if the length of this V1 is 2, okay, and then if the length of the other vector is, let's say, 1, okay, and then the length of the B vector is 4, let's say, right? So then how do you add these two V1, V2 vector together to get to your 4, right? So you have many possibilities. You'll find that actually, for example, you can have this 4V1 equals B, right? Or you can have 4V2 equals to B. Or you can have 2 times V1 equals B. Right? Or you can have 2 times V2 plus V1 also equals to B. So there are more than one combination that will get you to the black vector. There are actually infinitely many of them. So then what is the common feature in these two cases? Is that the two vectors, the black and blue, they are parallel to each other. So in other words, they are linearly dependent. Okay, linearly dependent. Okay, so this gives you either no solution or infinitely many solutions. So next, again, a homogeneous system that if I want to solve, now this time I've solved this equation, right? So, but this is not a finite B vector anymore, but a 0 vector. Okay. So then how do I find the solution of this one, right? So that means that I need to add some of this blue, right? So, and then with this sum of this red, and then at the end get to 0. So in this case, you could see that the only possible way that you can do it is that you set the scale of this blue to be 0, and then also set the scale or the length of this red to be 0, right? So then that's the 0, 0 solution, and that's the only possibility. So now the other case is that so this is what is this case, right? The two non-parallel vector, right? So this is the two vectors that are linearly independent. Then and again, the second case is that I have these two vectors to be linearly dependent. Right? So this time, how do I use this blue and then use this red to get to 0? Okay. You can find that actually there are infinitely many possibilities because you can use the blue vector to go however far you want, right? And then plus a negative of the red, right, to help you to go back to the 0. So there are infinitely many combinations that you can take, right? Just you go very far away, doesn't matter. Use the other vector to go back. So this case, again, infinitely many solutions. So next, we'll move on to the 3x3 case, but I think it's a good point to actually, let me just first lay out some definition. Okay, some definition that you might have already seen. At least I mentioned it in the last chapter. Okay, so the first concept is the linearly independence, right? So remember in the ODE chapter, I talk about the linear independence of the functions, right? And but I talked to you that actually the linear independence is really from linear algebra. It's really originated from talking about vectors. Okay. So then here let's lay out the definition of linearly independent. Okay. So when I talk about linearly independence, I always first need to give you a set of vectors. Okay, of course, in the previous example, I only give you 2, right? But 2 is a set. Of course, later we'll consider 3. Okay. But anyway, in general, it can be a set of vectors which contain n vectors. So from V1 to Vn. And then if they are linearly independent, so then you will have to So how do you find whether it's linearly independent? Is that you have to consider this equation here. Okay, so that means that you take the first vector, okay, give it some multiplication factor plus the second vector, give it another multiplication factor, and so on. Okay, so and then add all the n terms up. Okay, and if you find that the sum of this n terms is 0 only when you put all these coefficients to be 0, then that means it's linearly that means they are linearly independent set. Okay, so it's easy to think about the special case. Okay, so the two vectors and the three vectors. So if I have these two vectors in the XYZ three-dimensional space, okay, so two vectors are linearly independent, okay, if they are not parallel or anti-parallel. Anti-parallel just means that the directions are exactly opposite. Right? So that means if the two vectors are not lying on the same line, right? So then the two vectors are known as the linearly independent. Right? So this is something that I talked about multiple times already. Right? So what about three vectors? So actually three vectors, last time I also told you, right? So is that if I have a set of three vectors, okay, if none of these can be, none of the members can be expressed as a linear combination of the other two, then these three vectors are linearly independent, right? So, but remember the counter example I gave last time, right? So if I have this XYZ space, right? So if I have, this is my first vector V1, and this is my second vector V2, and then this is my third vector V3, which is also lying on the XY plane, then you realize that this V3 can be written as a linear combination of V1 and V2, right? So then in this case, these three are linearly dependent set, right? But only if your V3 is not this, right? But if it is like this, then this V1, V2, V3 is linearly independent, right? Because you cannot express any of the members by using a linear combination of the other two. Right? So geometrically, that's what happened, right? So for three vectors, they are linearly independent as long as they are not lying on the same plane. Okay. In the 3D space, if they are lying on the same plane, they're linearly dependent. If not, then they are linearly independent. So this picture, you can see what can you see here? So I have five vectors here. Okay. So I have five vectors here. Is it a linearly independent set? Okay. You can see that actually it is, because you can see that, okay, although all the four vectors here are lying on the same plane, but then this K is not, right? So that means this K vector cannot be expressed as a linear combination of the other four. Right? So this is a linearly independent set. So however, if you take the K away, okay, just consider these four vectors as a set, then this will be a linearly dependent set. Okay, then one other definition that is closely related is known as the span. Okay, so the span of a set of vector, okay, this is not from V2, from V1. From V1 to Vn, okay, so is that the span of this set, okay, is the vector subspace that contains all possible linear combination of this set of vectors. What does it mean by linear combination? Linear combination means this, right? So you take the first vector, multiply by some scalar factor, whatever you like, plus the other scalar factor, right? So to the other vector, and then add all of them, right? So this is known as the linear combination, okay, of all the vectors. So then the example is that if I have two linearly independent vectors, then it will span a 2D plane. Okay. So what it means is that as long as I have two vectors that are non-parallel to each other, it does not have to be perpendicular to each other, right? So it can be like this, okay, but let's say they lie on the same, the plane of the screen, right? So then any vector that you can think of in this plane of the screen, okay, can be expressed as a linear combination of this V1 and V2. Okay, you can always try to scale this V1 and then scale this V2 by some factor and then get to this vector here. Any vector on this plane can be done like this. Okay. So, and similarly, okay, if I consider the 3D space, is that if I have three linearly independent vectors, then it spans a 3D space. So again, what it means is that again, the most common example that you have already used a lot is that if I have a three linear independent vectors, which is the x hat, y hat, z hat. So this is a set of linearly independent vectors, and then it spans a 3D space. So that means that any vectors in this 3D space, right, can be expressed in terms of these three unit vectors here. Something you have used a lot already. But as I said, again, these three does not have to be really perpendicular to each other. This is, of course, a very nice choice, right? But for example, if your third vector is not z hat, but it's a vector that goes like this. Let's say this is z hat plus x hat. Then this is still okay, right? So these three vectors will also span a 3D space. Okay. So then another definition here is the so-called the basis. Okay, the basis of a vector space. Okay. So a set of vectors, okay, again from V1 to Vn, is the basis of vector space if they are linearly independent. Okay, and if they span the vector space. Okay. Just like as I said, right? So if you have the xy plane, right? So and then x and y will form a basis, okay? Because x and y are linearly independent, right? And then any vector in this xy plane can be expressed in terms of x hat and y hat. However, right? So this is not the only choice. Okay, if I choose x hat plus 2y hat and y hat, okay, this will also be a basis. Okay, so they are still not parallel to each other. But the third one is that this is not true. Okay, so x hat plus y hat and 2x hat plus 2y hat will not form a basis, right? Because you can see that you multiply the first one by 2, then you get your second one. So these two are linearly dependent. They're parallel to each other. So then for the three-dimensional case, right, of course, if you choose x hat, y hat, z hat, form a basis. And then if you choose this one, see that they will also form a basis. Okay, these three do not lie on the same plane. However, if you see this one, and this one, the three together, they do not form a basis, because you can see that this one is just a linear combination of the first two, right? Because if you just add the first one to the second one, then you get the third vector. So linearly dependent. So finally, okay, so the dimension of a vector space is the number of vectors. Okay, so in any basis, okay, that span the vector space. So that means that if you have a two-dimensional vector space, so the xy plane, right? So you can always find two vectors as your spaces, okay, but no more, no less. Right? So you cannot say that in the XY plane I can have these three vectors to be my bases, right? Because the three of them will be linearly dependent, right? So similarly, for the 3D space, right, the number of vectors to be your spaces will always be 3. Okay. So actually, let me, because the signal 8 will be issued soon, so let me ask people in the classroom. So do you prefer to continue or do you prefer to go home? Let me ask the people in the classroom. Continue. Continue or go home? Continue. Okay. Okay, then I'll continue. So that's so much about the definition. So, but these are all quite intuitive. Okay, so linearly independent, right, okay, basis. Now let's get to the 3x3 cases. Okay. So here, right, so I have this three equations, three unknown, right? So and again, non-homogeneous system. So in this column picture, right, so I write this again as a vector equation, right? So this time I have this three vectors, each vector has 3 components. So then in this geometric picture, right, so what I have, right, would be these 3 vectors in the XYZ space, right, the red, blue, and the green. Okay. And now, of course, on the right-hand side, this B vector is also a vector in the 3D space. Then again, the question is, I want to find the appropriate linear combination of these 3 vectors in order to get to this B vector. Right. So in this case, you can see how do we got that, right? So this red one multiply this to make it longer to be here, right? So and then this blue one you multiply to make it longer to be here, right? So then you get a vector that looks like this one. The red and the blue, right? The red and the blue added together is this. First of all, is this purple one, right? And then the green one make it longer to make it like this, right? So then finally, your purple add the green, right? Then you get to this black vector here. Right? So then again, this is an example of one unique solution, and you have 3 linearly independent vectors. You can see how I draw them, right? So they are these 3 vectors looks like this. Clearly, they are not lying on the same plane, right? So next example, right? So next case is that this time I have these 3 vectors to be linearly dependent. You can see that the red, blue, and green, they all lie along the XY plane. Okay. But this time the B vectors, right, I don't draw it anymore. So it's up here, right? Has some non-zero Z component, right? So no matter how you add these 3 vectors together, it's always stay on the XY plane. We are not going to get to this point. So then this case, no solution. So and then finally, the last case is that again this time I have this 3 vectors to be linearly dependent, because you can see that this red, blue, green actually all stay on kind of this plane here, right? All these 3 vectors stay on this the plane that I just draw. Okay, although they are not all staying on the XY plane, but still they lie on some plane. Okay, so then these 3 vectors, first of all, linearly dependent. However, okay, so this time you see that two of the vectors are directly pointing at the same direction as my B vector. Okay. Then that's why this time you will have solution, right? So you can always use this red vector plus this green vector to get to this point. Okay. Of course, in this case, blue will be useless, but still, you don't need to care about that. You can use two of them to get to your solution, right? And this time, again, you get an infinitely many solution, right? So same argument that I talked to you about, right? So you can take your green to go really, really far away, but then take the negative of the red to go back to this point, right? So many different possible combinations. So no solution, infinitely many solution. Again, I think I repeated too many times already, right? So this time, homogeneous solution, right? So you can, using the similar argument, you see that it either has one solution or infinitely many solutions. Okay. So now we have considered the two equations, two unknowns, right? We consider three equations, three unknowns, and then here what we have is three equations, two unknowns. Okay, so previous case we always have the number of equations equals to number of unknowns, but here, but in general they can be different. Right, so here number of equations greater than the number of unknowns. Right? Two unknown, three equations. But still, it doesn't stop us to think of them as the vectors, right? So this system can still be written as the vector form like this. Okay. So in this case, I have just two vectors, right? But these two vectors are living in the three-dimensional space. So and then I have to take the linear combination of these two vectors to get to this vector. In fact, in this case, it is still possible to have one of the three outcomes, either no solution, one solution, or infinitely many solutions. How is that happen? So here, the case you can see that if my red vector and the blue vector, they both lie on the xy plane, okay, but then my B vector has some non-zero z component, then this is no solution. So how do we have one solution? Right, so if you want to have one solution, what do you need is that you imagine that there's a plane. I might not be able to draw it very well, but imagine that there's a plane like this, okay, and this B point is lying on this plane, right? And it so happened that my two vectors, the red and the blue, also lie on this plane. Then you have that means this red, this blue, and then my B vector, they all lie on the same plane. Then you have one solution. Well, provided that this red and blue are still not parallel. So also, it's possible for you to have infinitely many solutions. Right? So you could imagine that if this blue and the red vector, they both point at the same this B point. Right? So then in that case, right, everything parallel to each other, infinitely many solutions. So then what about the other possibility? So is that this time the number of equations is less than the number of unknowns. You can see that in this case we have four unknowns: x1, x2, x3, okay, sorry, typo here. X4, 4, x4. So four unknowns, but this time I have three equations only. So then again, if I make it as the vector form, it will look like this. Okay, the linear combination of these four vectors equals to the B vector. And this time, okay, so there are two possibilities. Okay, either have no solution or infinitely many solutions. How do you have no solution? Again, imagine that all these four vectors are lying on the xy plane. Okay, but this B vector has a non-zero z component, then no solution. And infinitely many solution, right? So if you have if three of the vectors, right? So or if they are not just lying on the xy plane, right? So if just any one of them has some z component, then this time you can get to this vector. So, but in this case, okay, even you have solution, it will be infinitely many solution. Okay, not possible to have just one solution. Okay, because 4 vectors in 3D space, right? So that means that it's not possible that this set of 4 vectors is a linearly independent set. Okay. One of them, okay, will be able to express as a linear combination of the other 3. So then in general, right, in general, if I have this m equations, n unknowns, then geometrically, what we are doing is that I have m-dimensional space, right? So that means that, right, so each column vector has m components. So, and then in this m-dimensional space, I have n column vectors. Okay, so n column vectors. So each vector has m components. So then solving this set of equation means that I want to find all the possible linear combination, right, x1, x2 until xn, such that this whole thing equals B. So that's the geometric meaning, right, so according to this column picture. When you are solving this kind of equation, system of equation, that's what you are doing. So, and here the summary is that, again, I divide it into 2 cases, non-homogeneous, homogeneous. Non-homogeneous case, you always have 3 possible outcomes, right? No solution, one solution, that means one unique solution, or infinitely many solutions. And in particular, that's what we spend most of the time to talk about. If m equals n, so that means, right, 2 by 2 system or 3 by 3 system, m equals n. So then if in this case, if m equals n, and also if your n vectors are linearly independent, then a unique solution will exist. Okay. So otherwise, if m is not equal to n, right, so we need more information to determine. So then for the homogeneous case, there are 2 possible outcomes. Okay, again, one solution, and also known as the 0 solution or the trivial solution. Or the other possible is the infinitely many solution. So again, if this n vectors are linearly independent, then unique solution will exist. And that unique solution, of course, is the 0 solution. So otherwise, there will be infinitely many solutions. Here, any questions? No question? Probably too easy, is it? Okay. Okay, so let's try to. I'll just finish this part 1 of the chapter. We'll finish a bit early today anyway. Okay, so now we want to actually try to do some operation, right? To actually solve it. Right. So what we have done so far is just give you a bunch of pictures to think about the problem, but we we didn't actually solve a problem, right? Solve a system of equation. So if we want to solve a system of linear equation, right? So what we can do is that we write it in this so-called matrix form. Okay, so here I make an assumption that all of you know the basic calculation rules for matrix. So you know how to multiply the matrix by the other vectors. You know how to multiply two matrices together. You know how to find inverse. Okay, this is the assumption that I'm making. Okay, but if that's not true, okay, please let me know. But anyway, this equations written in this matrix form like this. So I have this n by n matrix and then this n by 1 column vector. And then this system can be represented as this so-called augmented matrix. So then the one way to solve this system of equation is to use the so-called Gaussian elimination. Again, I believe this is something that you have learned. Is that true? So Gaussian elimination is that it's composed of the following basic operation. Okay. So is that if I have this augmented matrix, right? So you are free to interchange any two rows, and then you are free to multiply any row by a number, a non-zero number, and then you can make addition of a scalar multiple of any row to another row. So, and the purpose is that with all these combinations of this operation, you are going to make this augmented matrix to the so-called row echelon form. Okay. This row echelon form looks like this. So what does it looks like is that first of all, if you have some rows that only contain 0, okay, you put it at the bottom. Okay. And also, the leading coefficient of a row, so that means it's the first non-zero number in one of the rows, okay, is always strictly to the right of the leading coefficient of the row above it. So what it means is that, for example, this is the second row, right? The second row, the first non-zero coefficient is this A22, A22 prime, right? So, and this is the second column. So one row above it here, right? So the first leading coefficient is over here, right? It's one column to the left. So then that's okay. So you could imagine that a row below this second row, the first leading coefficient will have to be at the third column, or the fourth column, or the fifth column. Okay, but it cannot come earlier than this. So then the rank of a matrix, so the rank of this matrix essentially is equals to the number of non-zero rows that you have after you make it into this row echelon form. So let's do an example here. Is that I have this set of equations. Okay, so it's the it will give a 4x3 matrix, right? So 1 here, 1 here, -2 here, and then 7 here, and so on. Okay. So 4x3 matrix. If we do Gaussian elimination, so what do we do? So here I label what operation that we have done to get to this. Okay. So what I'm doing here is that from here to here, what changed? R2 changed. What is R2? R2 is the second row. Okay. R3 also changed. You can see that R4 also changed. Right. So basically, how do you get to from here to here? Right. Is that I take this R2 minus 2 times R1. Then you get this 0, -3, 0, and -12. And then the third row, okay, you take the third row and then plus 5 times of the first row. Okay, then you get to this. So what is the criteria for us to do this, right? So the purpose of this is to try to kill the so-called the leading coefficients of the row below, right? So we want this to be 0, want this to be 0, want this to be 0. So that's why That's what we achieve. So after the first set of operation, I have this second, third row, fourth row to have this to have zero coefficient as the first term. Okay. So, but we are not done yet. Okay, so now we just multiply this, okay, by some factor such that these all becomes 1. Right. So for example, for this row, you divide the whole thing by -3, then you get 1 and 4. So for this row, you divide it by 9. So then 9 divided by 9 is 1. 36 divided by 9 is 4. So same thing for this. So now that you can see this, then you realize that you can kill more leading coefficient for the row below, right? So you can just the R3, right? So minus R2, then you kill this one here. Similarly, you kill the other one here. So, and at this point, you can see, what do you see, right? So the first row, of course, have all the non-zero numbers, and then the second row, right? So the leading non-zero is at the second column. And then for the third and fourth, they are all 0. So they all just put down here. So then in this case, the rank, okay, the rank of this matrix, right? So is 2, right? Because only 2 rows survive, right? They all become 0. So then now what you realize is that if you go back to write this system back to the normal form, right? Instead of the matrix form, right? So you realize that you only have 2 equations that are not being killed, right? So here you basically have x plus y minus 2z equals 7. And then the second one is y equals 4. That's it. Right. So from the beginning, where we have 4 equations, here, after all the eliminations, right? So you see that the system is actually effectively just 2 equations. Okay. So 2 equations, but how many unknowns? 2 equations, 3 unknowns. Well, you already know that you cannot have just one unique solution. So in fact, in this case, you can find that the solution looks like this. Okay, y is equal to 4. Okay, that's okay. But then the x and z can take this form. Okay, so there are infinitely possible pairs of x and z. Okay, as long as they are, both of them are related by this t. Okay. So what it means is that at the end, right? So if you go back to think about the row picture at the beginning, your solution is infinitely many points along a straight line in the 3D space. Okay. Okay, so here are some important facts. Is that if I have this system of linear equation, n by n system, then the following statements, the following properties are equivalent. Okay, so that means that if I say that the column of A span the n-dimensional vector space out to the n, okay, R means the real number. Right? So then that is equivalent to say that for any vectors B that belong to this n-dimensional vector space, okay, so B can be expressed as a linear combination of the column of A. And this is also equivalent to say that for any B vector in this n-dimensional vector space, this AX equals B has a unique solution. And also finally, it's also equivalent to say that the rank of A is n. And this slides is just talk about the conditions of having one solution, no solution, or infinitely many solutions for the non-homogeneous system or homogeneous system. Okay. So if the rank of A, okay, so is less than the rank of the amended matrix, okay, so then the equations are inconsistent and there's no solution. So I believe that these are the basic properties that you have also learned before. So then I'll just leave it for yourself. Okay, these three statements. But here instead, I'll just illustrate them by using examples. Okay. So here, example 1, right? So I have this 2x2 system. Then this is the amended matrix. After I do the Gaussian elimination, okay, I found that x plus y equals 2, and then 0 equals 3. So this is the inconsistency there, right? And then the rank of the A, okay, so is smaller than the 2, okay, smaller than 2. Because the rank of A, right? So what is the rank of A? Is that the number of row that is surviving? So this is just 1. So example 2 is that if I have this x plus y equals 0, x minus y equals 0, then again I have to do this Gaussian elimination of amended matrix. Okay. After that, you see that the rank of this matrix 2. Okay, and that's why this is having one solution. So finally, again for this case, if I do Gaussian elimination, okay, so what you have is infinitely many solutions. So in fact, usually we will have deal with more of a special case of this system of linear equation. So we were talking about m by n system, right? But here, if we have n by n, right? So then what happens is that the matrix here is a square matrix, right? So number of equation equal number of unknown. Then this system written as a square matrix. And if we have square matrix, the system can also be solved by finding the inverse of the matrix. Right. So for m by n matrix, we don't have inverse. Right. Only square matrix have inverse. Right. So if I have this a matrix system like this, right? So then the x can be just solved by, it's just given by the A inverse B. Right. And this is possible, right? So only if this inverse of A exists, and that also means that the determinant of A has to be non-zero. Okay. So, and in other words, right? So the existence of this A inverse is the indicator of whether the system has a unique solution or not. And again, if we just divide it into two cases, right? So for non-homogeneous system, right? So if this determinant A not zero, so that means that the inverse A exists, so that means a unique solution. So otherwise, the system can either have infinitely many solution or no solution. So we need more information. So for the homogeneous systems, so there are only two possibilities, right? Either unique solution or infinitely many solution. If this inverse of A exists, so that means if this determinant of A to be non-zero, then we have a unique solution. And you understand that the so-called unique solution is always just the zero solution, or the known as the trivial solution. Otherwise, the system has infinitely many solutions. So I think at this point, okay, so I've finished part 1 of this chapter, and I think I'll just stop here for today. Okay, so if there's any questions, okay, you can ask now. So any questions? If not, you are free to go. Okay, I see a question in the chat room. So the question is why the equation can be written as a vector form. So let me go back to the slides. So that means, for example, here, right? So the systems of equation written as this vector form. Okay, so it's because they are completely equivalent, right? So when I put it in this vector form, right? So at the end of the day, comparing whether two vectors are the same means that you are comparing each component individually. Right? When you compare two vectors, you look at the x component of the first vector, compare with the x component of the second vector. Right? That's the first comparison. Second comparison, you compare the y component of the first vector, compare the y component of the second component of the second vector. Right? So then, therefore, this is completely equivalent to this here. Right? So if it's not clear, let me just try to write it. So the left-hand side of this system, right? So the left-hand side of this system, you know how to add two column matrix together, right? So first of all, this x1, this constant x1, right? So go into each component of this column matrix or column vector. Right, so this one is completely the same as this one. And then these two column vector add together, right? It's component by component, right? So then that's why these two column add together is another column vector, which is x1 a11 plus x2 a12, right? So x1 a21 plus x2 a22. And this whole thing, right, so equals to this b. Right, so then as I said, right, first component equals to the first component of this first equation, right? Second equation, third equation. Yeah. Yeah, that's good. Any other questions? Okay. OK， 好。我或者我熄一熄嗰個 Zoom 先。